So for CCENT chapter number 2, we're going to be talking about network protocols and communication models. Essentially what this chapter is used for is for us to identify the rules for communication. Right? It's a little bit of a precursor to what we're going to talk about when we talk about the OSI model, the Open Systems Interconnect model. So this is a good fundamental chapter in allowing us to identify essentially how devices communicate with each other on the network. Right? Of course, think about communication in general, right? Any type of communication, picking up the phone and calling somebody, sending somebody an email, or communicating over the network using TCP/IP. We have to identify who the sender is. We have to identify who the receiver is. In networking, we do that with different methodologies, right? It fixes the stutter. Okay, I want, just to let anybody know, if you have audio issues, if you log out and log back in, it seems to fix that issue. Identifying the sender and receiver in networking can mean what is their source MAC address, what is the destination MAC address. It could mean what is the source IP, what is the destination IP, and so on. Also, you have to have a method for communicating, right? You and I, we're speaking English, right? That is our method of communicating. We have verbal eye-to-eye contact. We have verbal representations of understanding communication. Well, we do the same thing in networking. Devices have to speak a language, whether it's IP or IPv6, or if it's two routers talking EIGRP or OSPF. That is a method of communicating. Oftentimes, devices will communicate using other methods. They'll use things like TCP or UDP to identify what happens if communication fails, or what happens if communication doesn't fail, and so on. Common language and grammar, also part of that, right? Again, formatting of frames, formatting of packets, formatting of data fields, very, very important, right? The speed and timing of delivery. Now, if I came into this classroom and I just started talking really, really fast and told you all about networking, and that wouldn't be good, right? Because all of a sudden, you're trying to just focus on what I'm saying and trying to focus on keeping up with the message that you're not even getting the message, right? So speed, timing of delivery, very, very important. Oftentimes, confirmation and acknowledgement is important. If you're sitting there at the table and I'm sitting here telling you about EIGRP and you just have a blank look on your face, I can read that and I can say, okay, well, maybe he's not getting this because he's not acknowledging it through verbal communication or gestural communication. He's not saying, oh, yeah, I understand, or asking questions. So same thing happens in networking. When devices communicate in networking, oftentimes we have mechanisms built in that allow us to identify when the communication was successful or if the communication failed. So these are just fundamental components of communication in general. And this is how we ensure that messages are being delivered and being received appropriately. All right? Another major concept in communication is this concept of message size. Now, this we'll talk about specifically as it relates to networking communication. It is extremely important to restrict the size of information that you can send across the network. That doesn't mean total information you can send. It means how much data can I send in one segment, or how much data can I send at one time? Why is it important to restrict the size of information that I can send across a network? Let's say you want to send a 100 meg email. Well, let's be realistic. You want to send a 10 meg email, and he wants to do an FTP transfer of a 100 meg file. And you guys are connected to the same subnet, right? Well, there's only one way for you to get out of that subnet, and that's through your router interface that you're attached to, right? Because you guys are connected to a switch, that switch is connected to a router. That's one physical wire leaving the network. Well, if you didn't say, okay, you have to divide your 100 meg file up into small pieces, if he's sending his 100 meg file, guess what you have to do while that's being sent? You have to wait. You don't have the ability to transmit because you're waiting for his stuff to get passed through, right? So by establishing something called a message size, I can say, look, I don't care if you send 100 meg, I don't care if you send 10 meg. Both of you can only send 1,500 bytes at a time. That's called segmentation. It's also called, in Ethernet, an MTU, or maximum transmission unit length. So he has to take his 100 meg file and divide it up into segments. You have to take your 10 meg file and divide it up into segments. That doesn't happen at the application. It happens in the protocol stack. We'll learn more about that a little bit later on. But the purpose of defining a message size is to say, okay, everybody needs to use these common resources. So if we make the playing field equal, some of your segments can go out, then some of his segments, then some of your segments, then some of his segments, and then everybody gets access to those resources. Do you have a question?
Yes. So the segmentation happens on the switch itself?
No, it actually happens on the host,
on the host.
At the transport layer.
Transport, okay.
Yeah, we haven't talked about the OSI model yet, but segmentation occurs at layer 4, which is why when you refer to a component of layer 4, you actually call it a segment, because segmentation occurs at layer 4. Routers do something similar at layer 3, because routers function at layer 3, called, now it's escaped me, fragmentation, sorry. Not segmentation, but fragmentation. They're actually two separate things. They kind of do the same thing, but packet fragmentation happens at layer 3, whereas segmentation happens at layer 4. All right? So, and in IPv6, it's even completely different, right? And in IPv6, it only happens at the host. It doesn't happen on the routers. All right? We have a question online. I thought that segmentation is routers. That is not true. Segmentation is a function of layer 4. Fragmentation is a function of layer 3, right? So, and that's because, let's say you guys are connected to an Ethernet network, right? You have a defined set of rules that say, okay, the data, the size of the information that the host is generating has to be 1,500 bytes or less. That's pretty typical for an Ethernet network. But down the line, routers might be interconnected, and they might have different types of connections, like serial connections or wireless or whatnot, where the data has to be further divided because of restrictions on that length. That's when the router does fragmentation. Fragmentation occurs at layer 3. Segmentation occurs at layer 4. Routers don't function at layer 4, so they don't know how to do segmentation. They can only do fragmentation. All right? Typically, when we define fragmentation and segmentation, segmentation is something that's done at layer 4 from host to host, whereas fragmentation is done at layer 3 from router to router, between two routers. So when routers generate fragments, the other router on the other side reverses the process. Whereas in segmentation, the sending host divides the data, and the receiving host puts the data back together. Okay? You'll see that defined in a TCP header called well, we identify those segments by sequence number and acknowledgement numbers and so on. All right? And there's some windowing that takes place as well. All right, so anyway, we're getting a little bit ahead of ourselves because we haven't quite got into that concept yet. But segmentation, like I said, defines the size of messages. Now in IPv6, as I mentioned, fragmentation does not exist. So only the hosts can divide the data. We'll see more about that when we get into IPv6 a little bit later on. Each segment, it says here on the third bullet point, each segment is encapsulated in a separate frame with the address, information, and is sent over the network. Okay, that's true. There's a process in the host called the encapsulation process, where we add headers for each of the layers, and we send that data along the path. And then devices along the path read those headers to make forwarding decisions. All right? We'll see some graphics on that a little bit later on, I think even in this chapter here. All right, at the receiving host, the message is de-encapsulated, meaning we strip off all those headers and we put the data back together. We send it up to the application. All right? Now, the key to this is all based on something called an MTU. MTU stands for Maximum Transmission Unit Length. And it's typically defined based on what type of network you're attached to. Hosts are generally attached to an Ethernet network, so the MTU is 1,500 bytes. Whereas in wireless, it's 2,300 and something bytes and so on. There are different requirements for different types of networks. All right? The goal, of course, is to try to avoid fragmentation altogether. Segmentation cannot be avoided. That's always going to take place. Fragmentation is a further subdivision of the data, and that takes more time, more effort, more processing. So we try to avoid, fragmentation as much as possible. We're going to learn later on a method for using something called an ICMP echo request using extended functions to identify MTU sizes along the path. It'll be an interesting concept. All right? Now, what is the benefit? Segmentation means what? Different conversations can be interleaved. What do I mean by that? It's what I was describing, this concept where he can send some of his segments, and then you can send some of your segments, and somebody else can send some of their segments. That is the concept of interleaving information. Increased reliability in network communication. Well, maybe. Certainly it's going to be easier to deal with smaller data structures. The devices don't have to process as much information. The smaller data structures kind of lend itself to the fact that there's less likely of a chance that those data structures are going to get corrupted or lost somehow. And if you do lose data, it's much, much easier to recover that information, right? Than if you were to send everything in one large datagram, right? If you lose an individual segment, it's much, much easier to recover that individual segment than it is to recover your entire data, all right? There are some disadvantages, though. One of the biggest disadvantages, of course, is dividing the data up and putting it back together is complex. Because now each one of these segments has to be individually tracked, individually monitored, and of course, in order for us to reconstruct the actual data, I have to be able to identify where that segment goes in the stream and so on. And so we have some functions in TCP that allow that to happen, and some other functions in the application that allow it to happen if we're not using TCP. There's more overhead. Every one of these segments has to be encapsulated with its own headers. So instead of just sending one large datagram with one header, we're sending separate datagrams with individual headers. Now the overhead is relatively small compared to Ethernet, right? 1,500 bytes for a payload in Ethernet, 18-byte Ethernet header, maybe a 20-byte IP header, maybe a 20-byte TCP header. So it's relatively small compared to what we would see with the payload. But when you start to get into things like voice and other communications, real-time voice and real-time video, the payload sizes are much, much smaller. About 160 bytes for uncompressed voice using a G711 codec. Now all of a sudden that makes a big difference, that overhead. 160 bytes of payload, now you've got 18 bytes of overhead for Ethernet, plus you've got 20 bytes of overhead for IP, plus 8 bytes of overhead for UDP, plus 12 bytes of overhead for RTP. All of a sudden the overhead comprises a major portion of the overall transmission, right? So those are some of the downsides. When it comes to communicating over a network, there are essentially 4 different ways of communicating. Unicast, probably the easiest one to understand. Data is coming from an individual host going to an individual host. That's what unicast is, one-to-one communication. We will define how this is identified in the payloads when we start to get into things like Wireshark captures and we start talking about each of the individual layers. But there are unicast MAC addresses, there are unicast IP addresses, unicast IPv6 addresses, and specific port numbers for specific applications. Broadcast is when I'm trying to send information from an individual source to lots and lots of destinations, actually all the destinations. All right? There are special types of addresses that we use to send out a broadcast. Broadcasts generally are frowned upon in most networks today. In fact, IPv6, the concept doesn't even exist, at least not in a traditional sense. There is a way to broadcast an IPv6 using multicast, but we'll get into that a little bit later on. There are a lot of protocols that use this method for communicating, this broadcast method for communicating. DHCP, for example, a DHCP discover is a broadcast. An ARP request, address resolution protocol request, all these things we'll learn about later, that's a broadcast, all right? But here's a golden rule that I want you guys to understand. Broadcasts, even though they are used to communicate to all hosts, never, ever go through a router, ever. Layer 3 devices do not forward broadcasts, and that will never happen, all right? So if communication has to occur through a router, broadcasting is not a viable method, all right? Because routers always stop broadcasts. That's by design. That's one of the things that they're designed to do, is to not forward broadcasts. Multicast, now that's an interesting concept. Multicast is a routable packet, which means multicast can pass through a router. The destination multicast address is a virtual IP. It doesn't exist on an actual physical location. It's actually called a group address. So let's say that I want to deliver my message to lots and lots of people. Not all the people, but lots of people. I can generate my message and send it to a multicast address. And then anybody that wants to participate in that data communication can subscribe to that multicast group and receive that packet. There's a lot of things that have to happen in order for that to work. There are multicast routing protocols that have to be installed in the network. In Cisco, it's usually PIM, Protocol Independent Multicast. And then there are a lot of efficiency mechanisms that you have to build in, like IGMP snooping, Internet Group Messaging Protocol, and the hosts have to run IGMP in order to join or leave multicast groups. Right? Multicast is a little bit beyond the scope of this class, but let me just finish off multicast by saying it is a one-to-many communication model, meaning that several hosts receive the same message, but not all the hosts. And those green dots that are receiving that message, they're receiving the message because they asked for it. They subscribe to it, which is usually done through some sort of thin client or a web browser or something like that, or just simply by being a particular type of host. We're going to see multicast referenced later on when we talk about things like EIGRP and OSPF, because EIGRP and OSPF disseminate routing information using multicast. All right? Cast. This is an interesting concept. Typically used in IPv6. It was defined in IPv4, but nobody really used it. Anycast is a concept of one-to-nearest communication model. The easiest way to describe Anycast is to talk about something that everybody's typically familiar with, DNS, right? You guys know what DNS is. It allows our host to resolve names to IP addresses, right? When you go to your host and you configure your host for DNS, if you want to have redundancy, what do you typically do? You give them a primary DNS server, secondary, tertiary, maybe, right? But those are unique addresses, aren't they? All right? With Anycast, what we do is we assign an address to a service, like DNS. And every DNS server gets the same Anycast address. And when you program your host, you give that host that Anycast address. So with a DNS query, the infrastructure components, the routers, send that request to the closest or the nearest DNS server. All right? It's like a shared address. And it's obviously a lot more complex than that, but fundamentally that's what it is. And it's beyond the scope of this class to really get into the details of Anycast, but that's fundamentally how Anycast works. It's a one-to-nearest communication model. All right? One-to-nearest communication model. We don't see that too much with IPv6 or IPv4, as I mentioned. Now, protocols. We're going to spend a lot of time talking about protocols. Protocols are a way to define communication, like we saw in a few slides ago, right? EIGRP is a protocol for disseminating routing information. VTP is a protocol for disseminating VLAN information. STP, spanning tree protocol, is a protocol for identifying loops and preventing loops in the network. So these are different protocols that we use to communicate. The process of how devices share information. What do they do if there are errors or issues sharing that information, right? Setting up and terminating data transfers, very, very important. Daryl has a question, is TCP, UDP, unicast, or is it more complex? Unicast, the concept of unicast, broadcast, and multicast is typically limited to two different layers. The data link layer, which is where we have MAC addresses, and the network layer, where we have IP. TCP and UDP are host to host, meaning that routers and switches don't care about TCP or UDP, at least not fundamentally to make their decisions, all right? So when it comes to TCP or UDP, we don't define unicast, broadcast, and so on. There is no concept of that with TCP or UDP. The other thing that's important to understand is that these protocols don't ever operate independently of each other. If you open up a web browser and go to a web page, Cisco.com or thinKtanklearning.com, you're actually activating an application layer protocol called HTTP. Well, HTTP doesn't run by itself. As you move down the protocol stack, HTTP uses TCP. And TCP rides on top of IP, or IPv6, or some other layer 3 protocol. And IP runs on top of some sort of data link layer function, right? This is what we call the protocol stack. And every protocol that we use, now not all protocols go all the way up to the top of the stack. Some protocols stop at layer 3, some protocols stop at layer 7, some protocols stop at layer 2. But protocols interact with each other all the time. And this interaction is what we're going to be learning about throughout the next few hours. Zaid has a question. I have a question that has been always bothering me. Since ICMP is used in an IP packet, why is it a layer 3 protocol? Well, quite simply, IP is defined at layer 3. Internet Protocol and Internet Protocol version 6 and Internet Protocol Exchange, IPX, and AppleTalk, all of these protocols, and CLNS, all of these protocols are layer 3 protocols. ICMP is just another type of layer 3 protocol. The reason they're defined at layer 3, well, I suppose that's just how the makers decided to make it, right? It means that routers really play a huge role in transporting these protocols. But ICMP is defined as a layer 3 protocol because it has no layer 4 function, it has no layer 5 function, it has no layer 6 or 7 function. All right? Now, when we get into the protocol stack, particularly when we get into the OSI model, these concepts will make more sense, right? The OSI model is used quite a bit to define the interaction of protocols in a network. Hey, how about that? We're at the OSI model, all right? Now, there's a lot of stuff on this slide, and we're not going to, well, we'll hit all these high points, but we're not going to go through this in a lot of detail because we actually have chapters throughout the course that are dedicated to each one of these layers individually. So we'll spend a lot of time detailing what each of these layers do. First thing I want you to focus on is this section over on the right, because these are terms that are used in the industry to define the layer that we're referring to. For example, if I tell you what is the source address of the packet, what type of address am I looking for? Packets are defined as layer 3. So if I say, what is the source address of the packet, I'm referring to the IP address. Or I could be referring to the IPv6 address. Okay? A segment refers to layer 4. Now you know why we call them segments at layer 4. Because layer 4 is responsible for dividing data up based on MTU. All right? Everything above layer 4 from a networking perspective, particularly from a Cisco networking perspective, we don't really care. We call that data. Because layer 5, layer 6, layer 7, these are the layers that we typically associate to applications. And from a networking perspective, applications are not all that important. We tend to focus on routing and switching and that. Okay? All right? Now, it's not to say that there aren't terms used. Socket would be a term that would identify a layer 5 component and so on. But we pretty much focus on layers 1 through 4. At 1, we call them bits. At 2, we call them frames. We'll learn why they're called frames at layer 2. On the test, you'll see terms like that, right? They might not say, what is the destination MAC address? They might say, what is the destination address of the frame? And you need to know, based on the fact that they said frame, they're talking about layer 2. All right? Now, when it comes to defining communication, there are 2 predominant standards in the industry. There is the OSI model, which is called the Open Systems Interconnect model. It was developed by an organization called the International Organization for Standardization. And it defined the interaction of devices. It also defined the interaction of protocols. The stack, or the model itself, does not define specific protocols. For example, the model doesn't say, this is how IP works, or this is how IPX works. We have individual RFCs for that, request for comments. The model is a structured approach to defining the interaction of protocols. I'm going to explain what I mean by that in a minute, and it'll make perfect sense to you guys when I go through that explanation. We also have the host-based model, the TCP/IP model. This is more of a generic model, the one that you see on the right. On the test, you may have to be aware of how the TCP/IP model maps over to the OSI model. You might have to be familiar with that. But like, for example, the network access maps over to the first 2 layers of the data of the OSI model and so on. Both of these do essentially the same thing. They define the interaction of protocols. All right? Now let's break that down a little bit, because I think it's very important for you to understand. First of all, at the physical layer, which is layer number 1, this is cabling, connectors, interfaces. If it's a wireless device, antennae, whatever, right? Anything that has to do with transmitting the bits, the 1s and the 0s. We do have some devices that function at this layer. Now, I would not necessarily say that a network card should be classified as a layer 1 device because they have MAC addresses burned into them. But certainly network cards have a physical layer component, don't they? They have an RJ45 connector or a wireless antenna or something like that. Hubs function at this layer. Now, hubs are how we used to connect networks in the past. Back in the day, mid-90s, late 90s, we started getting bridging in the late 90s, and we started getting switching kind of around the late 90s, 98, 97, 98. But hubs are layer 1 because they have no intelligence. When you plug hosts into a hub, whatever goes into one port just gets spewed out of all of the other ports. It's voltage in and voltage out, essentially. All right? So we classify hubs as layer 1 devices. Some other devices, maybe a media converter. You guys know what a media converter is? Going from copper to fiber, for example. They have devices that allow us to interconnect those devices, those components. Some other physical layer devices, well, cabling, certainly. Connectors, patch panels. These are all kind of physical layer devices.
Is a transceiver one of them?
Transceivers, yes. A transceiver would be considered a physical layer device. Back in the day, On Cisco routers, we used to connect Ethernet using AUI. It's a DB15 connector. And you used to have to get these transceivers that would plug into the router to connect your thicknet cable, your 10-base-5 cable, to your router, right? And we call those AUI connectors or AUI transceivers, okay? The data link layer, which is layer 2, this is the first layer that we start to see some intelligence. And it comes in the form of what we call MAC, Media Access Control. Most of you are familiar with the term MAC address, right? Well, MAC address is just one type of addressing at layer 2 that provides media access control. Okay? MAC stands for Media Access Control, whether it's referred to or referenced in an address or other methods, right? But Frame Relay also has a MAC method. It uses something called a DELC, a data link connection identifier, and so on. PPP has different MAC functions like authentication and encryption and so on. All right? It says here LLC and MAC. I want to be very clear. Those two components of the data link layer are unique to one protocol, 802.3 Ethernet. So the LLC and the MAC sublayers are not defined in the data link layer for all protocols. Frame Relay doesn't have an LLC or a MAC sublayer. ATM does not have an LLC or a MAC sublayer. Even Ethernet 2, which we'll talk about later, doesn't have an LLC or a MAC sublayer. Only 802.3 Ethernet, right? We have things like frame check sequence. That's what the FCS stands for. Cyclic redundancy checks. And by the way, we're going to learn all about this. We've got a whole chapter on the data link layer coming up, all right? So I'm not going to get into a lot of detail on this right now, but as you can see, we have things like error detection. We have header and trailer bridging. We'll talk about what that means a little bit later on. But look at what devices function at this layer. Bridges and switches. Now that means that a bridge or a switch, which both of those devices they function exactly the same way. Bridges and switches make their decisions on what to do with data because of information at this layer. A bridge or a switch will never make a forwarding decision based on anything above layer 2. Does that make sense? So when I say a device functions at a particular layer, it means that it makes its decisions based on what's happening at that layer. So a bridge will never look at an IP address and say, I'm going to forward information based on this IP. A switch will never look at an IP address and say, I'm going to forward information based on this IP, because they don't understand IP. Everything above layer 2 is data. Okay? The network layer, which is layer 3 of the OSI model. This is where IP addressing occurs. This is where IP works. ARP, the Address Resolution Protocol. ICMP, the Internet Connection Messaging Protocol. These are all protocols that function at this layer, which means they use IP as their transport or IPv6 as their transport. All right? Now it says here, logical addressing. Well, let's talk about that for a second. We didn't see it denoted for the data link layer, but at the data link layer, oh, it is there. It's right in the first one, physical addressing. So we see physical addressing at the data link layer. We see logical addressing at the network layer. What does that mean? Well, it means that at the data link layer, addresses are tied to the physical device.
Is that the MAC address?
The MAC address in most cases, yes. Addresses are burned in to the device. Logical addresses are like IP. If you're connected at this network, your IP is X, but if you go across the street and connect to another network, your IP is Y. But your physical address doesn't change. Okay? Now, the analogy we use is your mailing address as opposed to your name. Your name follows you everywhere. It doesn't change. But your mailing address might change depending on where you move. Unless you're a criminal, then both might change, right? then you might change your name as well. All right. Also says logical addressing, fragmentation. Yes, fragmentation, not segmentation, fragmentation. Routers dividing data up into smaller pieces, called fragmentation. So the primary device that functions at this layer is a router. Now at this point, I generally get the question, well, wait a minute. What about a multi-layer switch? Or what we hear oftentimes as a layer 3 switch. I don't know if you guys have ever heard that term. Okay.
A router with a switch in the same device?
Yes, that's exactly what it is. It is not a special type of device that breaks these rules. It is just a router and a switch built into the same box. Think about it. The routers at your house that you get for your internet, that's basically a multi-layer switch, isn't it? It has a 4-port switch on the back, and it's also a router. So a multi-layer switch is not anything special. It is just a box that has both routing functions and switching functions built into it. Okay? Daryl has a question, would an access point be a, hold on, it's cut off. Let me move the chat window over here. Would an access point be a layer 2 device? Absolutely. Access points are bridges. That's why you often hear them called wireless bridges. Why do you think they're called wireless bridges? Because they're taking one physical layer medium and they're converting it to a different physical layer medium. They're taking wireless signals and they're converting it to twisted pair Ethernet, right? And in fact, if you break down the architecture of a wireless access point, it is actually has multiple MAC addresses. It has a MAC address per radio, has a MAC address, a base MAC address for the Ethernet connection, and it does switching. That's what its job is to do, is to take traffic from the wireless side and switch it to the Ethernet side. Now, I will say this. Traditionally, wireless on the radio side has been a hub. It's always been a switch in that taking traffic from wireless to Ethernet. But on the radio side, it's usually a hub, meaning that everybody is competing for that wireless airspace. All right? That's why when you connect to a wireless access point, traditionally, every time somebody connected to that wireless access point, the bandwidth got cut in half. Because you have this contention algorithm called CSMACA, Carrier Sense Multiple Access with Collision Avoidance, which had time slots and whatnot for transmitting over the wireless radio frequencies. But only one person could transmit at a time. All right? So there is a layer 1 function. Now, we do have smarter devices now that have what we call MIMO, multiple input, multiple output. So you're getting full duplex communication with wireless, but and that's when you get into 802.3ac and 802.3n to get those functions. The last layer I'm going to mention on this slide is the transport layer. No devices at this layer. But this is what we call a host-to-host layer. Why would I call it the host-to-host layer? Do routers care what happens at the transport layer? No, because they function at layer 3. Do switches care what happens at the transport layer? No, because they function at layer 2. So the only devices that actually care about what happens at this layer are hosts. PCs, computers, which is why it's called the host-to-host layer. We have 2 protocols that function at this layer, TCP and UDP. That's pretty much what's been defined. Not to say that somebody couldn't come up with their own layer 4 protocol later on if they so choose, but that's what we have defined. Okay? And of course, you see a lot of notations there. Fragmentation, all right? I don't like that term. I probably should change that. Should be segmentation, not fragmentation. Sequencing of data, reliable delivery, error recovery, flow control, all functions primarily of TCP. But again, tomorrow we're going to go through a chapter on TCP and UDP. Everything above that, we don't really care too much about from a networking standpoint, an infrastructure standpoint, session, presentation, application. Those typically relate directly to applications. You take a Microsoft class or something like that, a programming class, you might be concerned about what happens at those layers, but from an infrastructure standpoint, we don't really care. All right? Now there is layer 8 and layer 9. Layer 8 is budget, and layer 9 is politics. Sometimes we have to deal with that, but usually we don't see that depicted in our OSI model. All right? If you're a network engineer, you have to deal with those two layers all the time. And they're usually the most troublesome layers. So what is a PDU? A PDU is a protocol data unit. It's basically what we use to define the whole thing. All right? You got somebody on a computer that wants to send an email. All right? They're in their application, Outlook or whatever, and they're generating the email. The email is going to end up in some sort of data being generated. Now that is going to start to be sent down the stack, what we call the protocol stack. And this is all happening within the computer. The computer knows it's on an Ethernet connection, so it knows it needs to divide the data up into smaller pieces. This happens at layer 4, and this is called segmentation. Each of the raw data gets divided up. Now, at this point, every single one of those components is treated independently. So they all go through the process of having headers applied. Transport layer header gets applied. Network layer header gets applied. And the data link layer header gets applied. This is called encapsulation. What are the headers for?
The headers which has the recipient's information.
Well, they have all kinds of information in them, right? They have the recipient's information. They have the sender's information. They have QoS values. They have time to live values. They have a lot of stuff in them, right? The headers are used by the devices in the network to make decisions, right? And what device is going to use this header to make a decision? A router, because that's the layer 3 header. What device is going to use this header to make a decision? A switch, because that's the layer 2 header. What device is going to use this header to make a decision? A host, because that is the transport header. So the headers contain information necessary to get the bits from here to there. Now, depending on what kind of devices are in between will depend on how much of this data has to be processed versus not. If you're going from one host to another in the same LAN, the same network, the only header that ever gets processed is the frame header. Everything else is just data. By the way, we did notice that at the data link layer, it was called a frame. And that is because this is the only layer that adds a header and a footer. All right? It says frame header on the back. I don't know why, but that should be frame footer. We're framing the data at both ends, which is why it's called a frame. All right? We'll talk about what goes into that footer a little bit later on. All right? Now, this process is called the encapsulation process. As we go down the stack, we add all this information to our device, or to our data. Eventually, it gets converted to ones and zeros. It gets sent across the wire. Now, what do you think is going to happen as we move back up the stack on the other side?
From the bottom to the top.
Each of those headers start to get stripped off until finally we have these pieces of data we put back together, we send it back into the application on the other side. That's called de-encapsulation. Now, when it comes to transporting data across the network, we have essentially two types of devices we have to deal with. We have routers and we have switches. Hold on, let me mute this person. I have to see who it is. Is that it? I think that was it. Okay. So we have routers and we have switches. Now routers, of course, we know because they're layer 3 devices, they're going to use source IP or destination IP address Well, really, they only use destination IP to make a decision, right? And we're going to learn all about how that happens later on. And then we have our data link layer, right? Source data link address, network data link, or destination data link address. Switches use that information to build their databases and to make their forwarding decisions. Okay? All right. When we're communicating with devices within the same network, what essentially do we need to be able to do that? The only thing we need to communicate to devices within the same network is a MAC address. Because the only type of device that we're going through to reach the destination is a switch. So all of this other information that you see here, at least at layer 3, is kind of superfluous, right? Because the switch is not going to use that information to make a decision. But it's safe to say that application developers aren't going to write their applications to function differently in a LAN than they would over a routed network. So everybody kind of uses the same format, right? Now, if you want to communicate outside of your subnet, very, very important. All of a sudden, the network layer becomes very important. PC1 doesn't send its information to a local host. It sends its information to something called the default gateway, and then that default gateway forwards that information using IP routing. All right? And of course, we'll learn all about IP routing a little bit later on. Okay. All right. Now, there are a bunch of organizations. Well, we've already talked about or alluded to this concept that there are a bunch of ways that devices communicate. There are a bunch of protocols that exist, a bunch of communication methods that exist, and so on. So we do see a lot of different organizations that really define the standards for how devices communicate, right? IEEE, for example, you see an 802 specification. That's IEEE. By the way, does anybody know what the 802 means? IEEE is responsible for managing standards for lots and lots of different industries. Obviously, the electronics industry, telecommunications industry, and so on. And they have these forums that define these standards. Well, the forum that defines standards for network communications was actually developed in 1980 in February. So 802 is February of 1980. Right? 2 is February. 80 is the year, right? And then you see the sub-specifications like 802.3, 802.11, etc. Those are just different working groups or within the IEEE organization. Not that you guys need to know that for the test, but it's interesting nonetheless, right? IETF. IETF is, well, they handle OSPF, right? And many, many other protocols, but in fact, they also have now started governing EIGRP. EIGRP used to be a Cisco proprietary protocol, but now it's managed by IETF. It's still owned by Cisco and still controlled by Cisco, but it's become an open standard. The Electrical or Electronic Industries Alliance, Telecommunications Industry Alliance. These guys typically define physical layer standards, cabling standards. We'll talk about EIA, TIA 568A and 568B later on. We get into the physical layer. NIST, the National Institute of Standards and Technology. We do a lot of training for the Department of Defense and the United States government. So they're very familiar with NIST. They define a lot of the standards that we see in security realms today. International Telecommunications Union, ICANN, Internet Corporation for Assigned Names and Numbers. These guys are responsible for things like Cisco.com and thinKtanklearning.com and so on. Domain names, right? But the big mama the IANA, the Internet Assigned Numbers Authority. These guys are responsible for anything that has to do with public addressing on the Internet. Could be IPv4 addressing, could be IPv6 addressing, could be BGP autonomous system numbers, could be MAC addresses, right? These guys, anything that has to do with some sort of registered number on the Internet, these guys manage. Even port numbers, TCP and UDP port numbers are managed by these guys. Okay? Now, these organizations are generally not-for-profit. They're not tied to any particular country, you know, but obviously a lot of the Internet today has its foundation in what was developed in the United States in the 70s, right? When we had Stanford University and the Department of Defense developing DARPA and the Defense Research Project developing communications. The very first communication that took place was a telnet session, in transferring characters over a telnet session, and it didn't work. It failed miserably, actually. But, okay. Now, another thing that we'll be talking about, and we'll be seeing quite a bit, actually, is a network analysis tool called Wireshark. Wireshark is a tool, you can get it from wireshark.org. It's a free tool that allows you to do packet captures, PDU captures, so that you can analyze that information and take a look at what's happening in that information, or in that process. Now, it's very important, and we are going to spend a lot of time looking at captures, because essentially, the capture shows us the formatting of the headers, whether it's a layer 2 header, a layer 3 header, layer 4 header, or whatnot. We won't actively use Wireshark in the course. We'll see screenshots of a lot of Wireshark captures, but of course I'll point out all the components of Wireshark and what these numbers represent. By the time we're done with the class, you should have no issue opening up Wireshark and being able to interpret Wireshark information. All right, so that concludes chapter number 2. Chapter number 2, of course, was an introduction. Now we're going to get into chapter 3 in a little bit. We're starting to get into some of the layers, in fact, the physical layer, data link layer, and so on, and the OSI model in more detail.